Today, we begin a new topic called electric heating. Electric heating is a very powerful alternative to conventional methods of producing heat, like burning the coal, burning wood, etc., etc. However, before going into the topic of electric heating, let me first talk about heat itself a little bit. The transfer of heat, you may have already studied a little bit about it in the past. The transfer of heat happens through three different mechanisms: conduction, convection, and radiation. Let me discuss these three modes of heat transfer because they are invariably going to be a part of discussion, any discussion on electric heating. Radiation is a method of heat transfer that involves no contact between the source and the heated object. Sun does provide heat to planet Earth all the time through radiation. That's one example. Okay. In conduction and convection modes of heat transfer, physical contact does happen. Okay. In case of conduction, you will see that particles move at a microscopic level. They collide with other particles and transfer heat. Okay. There's not much of diffusion in this case. By the way, any heat transfer includes, in general, all the three methods. Only thing is, depending on the case involved, one method may be predominant compared to others. So, microscopically colliding particles, which include molecules, atoms, electrons, they transfer the heat energy, essentially speaking, within the material. Typically, conduction happens in solid materials, but it can happen in liquids also, and gases also, at least up to a certain extent. Okay, we'll come to the mathematical formulas soon for these three different modes of heat transfer. Convection is because of the bulk movement, which is diffusion of molecules within fluids. Typically, convection happens in liquids or fluids, much more than anything else. Okay. Now, how do you model these modes of heat transfer? I've taken all this from various sources. You will get the document. Now look at conduction carefully. It's definitely encountered very frequently in most heat transfers. Based on experimental observations, a long time ago, Fourier came up with an approximate theory for heat transfer via thermal conduction. Heat transfer in general can happen in three different directions, but we will limit our discussion to 1D case only. It gives you the basic idea at least. What Fourier did was, let's say he assumed, let's say that we have a rectangular block of some material as shown here. The top and bottom are assumed to be perfectly insulated thermally so that no heat transfer occurs from those two faces. And same thing also applies to the front and the back. Only the side faces are allowed to have heat transfer. The left face has a temperature T1 measured in Kelvin. The right face has temperature T2 measured in Kelvin. Okay. The length between left face and right face is capital L. We are assuming that length L is along the x direction. The rate of heat transfer, which is written in joules per second, small q with a suffix x. Depending on where you look, you may find different notations for this. Somebody uses capital Q, somebody says dq by dt. So all kind of things are there. I am taking qx based on the book that I was reading about this topic. So the simple formula, rather than going through differential equations, etc., I'll give you the solution that we may need. The rate of heat transfer in such a block of material first of all, whatever I was telling you is written here. Okay, you may want to read this. One side, that is the left side, is at T1, which is higher compared to T2, which is the temperature on the right hand side. Okay, other walls are all perfectly insulated. Now the formula is this. Rate of heat transfer from left face to right face is given by this approximate formula. K is a constant of proportionality known as thermal conductivity of the material. It is given to us for a given material. A is the area of cross section across which the heat transfer is taking place. T1 is the temperature on the left face, T2 is on the right face. We are assuming T1 to be greater than T2. If you don't do that, then minus sign has to be put in the equation. But we are avoiding complicating the equation unnecessarily. L is the length of the face, or length of the distance between the two faces. Okay. The units are simple enough. A is in meter square, T1 and T2 are in Kelvin, L is in meters, and Qx will be joules per second, which is watts. Sometimes they say watt per meter square. Then you calculate Qx divided by A. Okay, that's also done in many cases. I'm going to ignore problem 1 for now. I'll come back to it if time permits. There's a very useful concept related to conduction. Let's look at the equation again. Fourier equation. Qx equal to Ka multiplied by T1 minus T2 and the entire thing divided by L. We can rewrite this as T1 minus T2 equal to some hypothetical constant RTH multiplied by Qx. RTH is known as the thermal resistance of the material, and it is obviously given by L upon Ka. This concept is used especially when you have more than one material coming together during the heat transfer. Then we calculate thermal resistance for each layer and sum it up to get the overall thermal resistance. I'm avoiding theoretical derivations here. Okay. It may not be that important in this course, but in many other courses, I'm sure you'll be seeing this concept again and again. A thermal resistance is the electrical equivalent. I mean, the concept of electrical resistance has been brought into thermal discussions, essentially. It essentially means for a given rate of heat transfer in watts, what is the temperature rise? That connectivity, that connection between the two is what is described by thermal resistance. Now, simple problems. Problem 2 is quite a simple application of this equation. It says determine the rate of heat transfer by conduction per unit area. That means Qx divided by A for a furnace wall made of fire clay. The thickness of the furnace wall is half a foot. 1 foot is 1 foot is 12 inches. So half a foot will be 6 inches. Each inch is 2.54 centimeters. Okay. The thermal conductivity of the furnace wall clay is 0.3. The units are watt per meter Kelvin. That you can see from the equation itself. The furnace wall temperature, that is the inside of the furnace, can be taken to be the same as the furnace operating temperature, which is 650 degrees Celsius. The temperature of the outer wall of the furnace is 150 degrees Celsius. To calculate the rate of heat transfer in watts per meter square. First thing you do is write down the values given to you. K is 0.3 watt per meter Kelvin. T1 is 650 degrees Celsius. Higher value is always T1. Let's be clear about it. So you convert that into Kelvin by adding 273 to it. T2 is 150 degrees Celsius. Add 273 to it to get 423. Okay. The length is half foot, which is 6 inches, which becomes 6 multiplied by 2.54 centimeters. Divide that result by 100 to get meter. So half a foot is 0.1524 meter. Then you use this formula. Qx divided by A is K into T1 minus T2 divided by L. 0.3 T1 minus T2 is obviously 500 Kelvin divided by L, which is 0.1524 meter. So the answer is 984 watts per meter square approximately. In some cases, they'll give you the area and then they would like you to calculate the total wattage. Then you use A, you take A on the right hand side of the equation. Another problem is the wall of an industrial furnace is constructed using 0.15 meter thick fire clay brick having thermal conductivity of 1.7 watt per meter Kelvin. Measurements made during study. By the way, in all these problems, we are not worrying about transient behavior. When the furnace is starting, what happens in the initial period is being ignored. We are talking about steady state operation. So measurements made during steady state operation reveal temperatures of 1400 Kelvin and 1150 Kelvin at the inner and outer surfaces. Inner surface obviously will have higher temperature because that is where you are supplying the heat. But even the outer surface will not be that cold, despite the fact that you have put insulation, etc. in between. So the inner temperature is 1400 K, the outer temperature T2 is 1150 K. Calculate the rate of heat loss through a wall which is 0.5 meter by 3 meter on a side. So the area of cross-section through which you are supposed to calculate the wattage loss by heat, wattage loss by conduction, is 0.5 multiplied by 3 meters square, which is 1.5 meters square. Thermal conductivity is given as 1.7 watts per meter Kelvin, and length is given as the thickness of the material, 0.15 meter. Plug in all the values, you get 4250 joules per second or watt. That's the answer. Now the third problem is more realistic. Usually you have more than one material present in furnaces for practical reasons. Let's see how to handle this. Calculate the rate of heat flow through the vertical walls of a boiler furnace of size 4 meter by 3 meter by 3 meter height. The height is 3 meter, and it's a rectangular boiler. The other two dimensions are 4 meter and 3 meter. The walls are constructed from an inner fire brick wall 25 centimeter thick and having thermal conductivity of 0.4 watt per meter Kelvin. A layer of ceramic blanket insulation after that. On the wall you have a insulation of ceramic blankets which has conductivity of 0.2, and the thickness of that layer is 8 centimeter. And finally a steel protective cover is there which has thermal conductivity quite high, 55. Obviously steel conducts much better compared to other materials. So the steel thermal conductivity is 55 watt per meter Kelvin, and the thickness of the steel is quite small, 2 millimeter. The inside temperature of the furnace is 600 degrees Celsius, and the outside temperature is 60 degrees Celsius. It's cool enough on the outer wall. Calculate the interface temperatures between the layers and the overall rate of heat transfer, overall rate of heat flow if you want. First thing you do is calculate the area of cross-section through which transfer is happening. So you ignore height, you take the other two dimensions, 4 and 3 meters, multiply them, get the area as 12 meters square. Now there are 3 layers, I'm showing them here. T1 is the inside face of the boiler. After that you have fire brick, then you have the insulation, and then you have the steel protective cover. We are calling the temperature on the left side as T1 and temperature on the right side as T2. In between, we are calling it T3. Okay, that's the convention normally. So for fire brick, L1 is 0.25 meter, A1 is 0.4. For steel, which is the outer part, L2 is very small, it's only 2 millimeter, which is 0.002 meter. A2 is actually quite high, 55 watts per meter Kelvin. In fact, the reality is that the temperature T2 will almost be the same as the temperature on the right hand side of the insulation. The steel will hardly see any temperature drop. It will have almost the same temperature because of its high conductivity. That will be captured in the equations also. For insulation, I am using the symbol 3. L3 is 8 centimeter, which is 0.08 meter, and A3 is also given as 0.2. Lower conductivity means more insulation, as simple as that. T1 and T2 are given. You can convert the values into Kelvin. Now, in this case, because we have so many layers, the method is to calculate the individual thermal resistance for each of the layers and sum them up to get the overall thermal resistance. So for layer 1, thermal resistance definition I have already given you. It is L1 upon K1A. For layer 2, which is the outer part, it will be L2 divided by K2A, and in between, the middle layer is called third layer, which is L3 divided by K3A. So put in all the values, calculate the overall thermal resistance. Hopefully there is no mistake in my calculations. The middle layer, sorry, not middle, the number 2 layer has very small contribution to thermal resistance because conductivity is very high. Steel has very high conductivity. Anyway, the total thermal resistance turns out to be 0.08542 Kelvin per watt. Using that, what you do is use this formula Qx equal to Ka T1 minus T2, but you simply take the summation of all the individual thermal resistors, individual thermal resistances in the denominator. This is the formula to calculate the overall rate of heat transfer. T1 minus T2 divided by the total thermal resistance, which we have calculated as 0.0854. In this course, you may not be encountering such situations a lot, but still, conceptually, you should be aware that more than one material can be handled using Fourier's formulation, as long as you are willing to calculate individual thermal resistances and then you sum them up. The individual temperatures at the various interfaces can also be written like T2 minus T3 magnitude is simply the value of Qx that you have calculated multiplied by the thermal resistance of the material between them. Between 2 and 3, I have got T2 will appear at the end of insulation. So between T2 and T3, T3 is at the end of the fire break. So between T2 and T3, you will see insulation rather. So you use RTH3 for that and do the calculation. 210.72 Kelvin is the difference between T2 and T3. And similarly, you can do the calculation for the other section also. The temperature difference turns out to be 329.26. The total of these two plus small drop on the steel itself should give you the T1 minus T2 value, which is 873 minus 333. You can double check that. I think we are getting that. Okay. So this is the theory as far as conduction is concerned. Theory in very brief. How about convection and radiation? Convection. Heat is transferred by convection in, for example, immersion type of water heaters, where you have a rod which is immersed in water. There convection takes place all the time. Okay. Some conduction may be happening, but most of it is in the form of convection. Now, supposing you have a vertical surface which is hot, okay, and it is situated in air. The formula in this case for calculating the heat dissipation in watts per meter square is this. Proofs are available in physics books. 3.875 multiplied by T1 minus T2 raised to the power 1.25. Remember, conduction was directly proportional to T1 minus T2. Convection is actually proportional to T1 minus T2 raised to the power 1.25. T1 is the temperature of the heating surface. and T2 of course is the temperature of the air in which you are trying to send the heat. So this is an approximate model that we use for calculating the rate of heat flow through convection. For radiation also, formulas have been worked out. This particular one all these constants have been calculated in several textbooks. But here important thing is that now the fourth power of temperature gets into the game. In case of radiation, the heat transfer is dictated by fourth power of the temperatures involved. T1 is the absolute temperature of the radiating surface, fine. And T2 is the absolute temperature of the observing surface. And 5.72 into 10 to the power 4 is a constant which is derived mathematically. On top of it, there are two constants which capture the reality, eta and epsilon. Eta is known as radiation efficiency and epsilon is known as emissivity. Eta is 1 for single element and it has to be less than 1 if you have several elements side by side. The practical value is between 0.5 and 0.8 for more than one element. Emissivity is going to depend on the nature of the heating element. If you have a perfect black body, then emissivity is 1. For resistive element, this number is almost 0.9. These are practical values. So this is roughly what we do for calculating the rate of heat transfer using the three different modes of heat transfer. Now come to electric heating. Why are we pushing the idea of electric heating? There are several advantages and some disadvantages also. Electric heating is very common nowadays. It is clean, there's no dust or ash that is produced. So no cleaning cost is there. If you use coal or wood, obviously cleaning has to be done much more. Because ash will be there and dust would also be produced in the process. No harmful gases come out of electric heating. So you don't have to worry about taking them out of the system. Okay. Control is much more flexible when it comes to electric heating. You simply increase the resistance, decrease the resistance. In case of wood burning or coal burning, control is there, but it's not that smooth, that's for sure. So accuracy of control is much better if you are using electric heating. You can have fully automatic systems also where temperature is maintained almost at the constant value that you want. Repeatability is also better. Mathematical models for electric heating are a lot more accurate. It doesn't require much maintenance, not day-to-day attention. Electric heaters work, once they have been installed, you don't have to worry about maintaining them too much. If there are special heating requirements, generally wood and coal will not be able to do the job. Efficiency is higher apparently, wastage is lower in electric heating. One main disadvantage of electric heating can be that it is more costly. But of course, the advantages are also there. So in the long run, maybe it is not that costly also. Now there are two conceptually different methods of electric heating. One of them is direct, the other one is indirect. In direct heating, you pass the current through the material itself. to heat it up. In the indirect method, you pass the material through, you pass current through some other material, which produces heat, and then through convection, that heat comes to the material that you actually want to be heated. Okay, under each category, there are several options. We will come to that slowly. This is a direct heater using a resistance through which current is going, and I square R formula is being used to calculate the electric power dissipated, which will be roughly the heat produced, the rate of heat transfer that would occur will be almost what you will get from I square R calculation. Some losses will be there, I know, but by and large, I square R is a good indication of how much power would be generated from the heater. And this is one specific case where you see some practical values. This heater has dimensions 9.5 inch long, 10.25 inch diameter, and length and diameter are given. And I guess 16.5, I don't know what it is. This must be the third dimension somewhere. Fine, okay. Power supply is single phase, 230 volt. Temperatures that you can get from such a heater can be as high as 1200 degrees Celsius. Okay. The weight is 1 kg, wattage rating. Watt that you can easily produce out of it is 1.5 kilowatt, 1500 watt. Weight is 3 kg. Crucible spelling is wrong. I'll come to that word later. But crucible means essentially where the action is, where thermal is being produced. One crucible is there in this particular case. There's a lot of methods under direct heating. I'll be showing you another PPT, my own PPT, where we'll be discussing them in detail. But for now, just take the fact that direct heating and indirect heating are two conceptually different methods. In indirect heating, current is passed through a wire or other high resistance material, forming a heating element. The heat, which is I square R loss, so produced, is transmitted by radiation or convection to the body to be heated. The body to be heated never gets current in it, which may be necessary in many practical cases. Because you don't want to damage the sample which you are trying to heat in many cases. In that case, indirect heating is the only option. Immersion water heater is where water is not directly seeing the current. It is the rod which is seeing the current, and that is supplying heat to water using convection. Okay, domestic water heaters, you all know this, we call them geysers. This is the construction. A lot of things are there. Automatic controls are there so that a particular temperature is reached and then the device shuts off automatically. Shut-off valve is there to stop the supply of water once the cylinder is full. Generally, more than one heating elements are used inside. They need to be replaced frequently because of practical problems like deposit of material on them, their resistance getting weaker and weaker with time, etc., etc. There's a lot of practical detail about this water heater. If you open one up, you'll see things inside. It's one of the most popular applications of electric heating. Okay. The word used for resistance is element. And as I said, typically more than one elements are there. We'll come to this topic again later when I go through my own PPT. I'll tell you a lot of practical things about elements, resistive elements in particular. Indirect heating, eddy currents are one method. Okay, they produce heat. Indirect heating in general is not that efficient, but we still have to use it in a lot of cases. One very interesting technique for producing heat in, let's say, wood or any material which is not very conductive is so-called dielectric heating. What we do is we apply very high voltage across the material, and it produces, and it is high frequency voltage, not 50 hertz. It produces sufficient heat inside the material to heat it up in a very gradual manner, which is what we need in many applications, like, the furniture which is made out of wood generally needs this kind of processing to make the furniture long lasting. Okay, so lot of furniture manufacturers actually subject their product finally to this kind of heating to make the furniture lot more long lasting for sure. Okay. There are medical applications also. A patient suffering from problems, let's say in bones, needs his bones to be heated. Obviously, you cannot supply current directly to the body. So you use high frequency voltage across the bone. The value of voltage is low, but frequency is high. Produces enough heat, not too much, but not too less. So you can have accurate control of heat through the bone. Medical electronics uses this technique a lot. I'll be talking about all this in the next lecture in detail. Okay. Now, this we have already gone through, but it's written in this document also. Conduction, convection, radiation. I've given you this formula already, which is written here also. Even for convection, the formula that I wrote is given here as well. For radiation also, the formula I gave you is written here, which is good. Okay. Okay, we'll come to resistive ovens later. I want to show you something other than that. Induction heating, I'll come to that later in my own PPT. Let's ignore this for now. These are the two books where more details are available. You don't need that in this course, but for future I'm giving these two references. Book by Thareja and book by Taylor. They have a lot of details about electric heating. As far as this course is concerned, I think what I am giving you is enough. You don't have to worry about reading these books. A second document is also there, not mine, of course. The author's name is given below. Okay, this is the name of the author. He has produced a very good document on the same subject. A lot of information here is actually duplicated in the previous document also, and in my own notes also, but it's worth reading it. Heat is vital to day-to-day life, you know it. As mechanical engineers, you appreciate that even more than electrical engineers do. Okay, so this is popular information written in the first paragraph. Electric heating is superior compared to heat produced by coal, oil, natural gas, etc. Advantages are again given here. They were given in the previous document also. Virtually the same things are mentioned in this document. He is calling electric heating economical. Maybe it is, in the long run at least, because it doesn't need much maintenance, cost, etc. But in the short run, you pay a little more compared to oil heating or coal heating, etc. But it's definitely very clean method compared to the other methods. And accuracy of control is much better here. Uniformity is also much better. Automatic circuits can be designed to shut the whole thing right away, which is not generally possible if you are using oil heating or wood heating, or if you are burning coal. It's not easy to shut down coal burning right away. Electric heating is easy to shut down anytime. Other side of the story is that if there is failure of electric power, then you cannot heat. That is one disadvantage of this method. While wood, coal, oil heating would continue to work even if electricity fails. The industry has that solution as a backup all the time. Noise is less in electric heating. Fine. It requires less area to mount electric heating equipment compared to other methods. High temperatures are easily obtained here compared to other methods. Safety is better, I suppose, as long as you are trained in handling electricity. It is expensive to operate, yes, that's what I was saying. Electrical hazard of shock and fire are an issue. Yes, that's a disadvantage. You got to be super careful here. Technicians have to be trained properly. Modes of heat transfer, I think we have gone through it several times. He is also giving the same information. Heating element requirements, I'll come to that later in my own PPT. Yeah, this tree is what I wanted to show you really in this document. This is a very wonderful thing he has given. A complete description of all methods of electric heating. There are two conceptually different methods. One is at 3 Hertz or 60 Hertz, the other is at high frequency. And under each category, you will have indirect and direct heating. Okay. In fact, before that, he is breaking up the low frequency heating, which is power frequency heating, into resistance and electron bombardment heating. Electron bombardment is another story. I'll come to that later. And arc heating, where you produce an electric arc for a moment to produce the heat. That also, I'll be going through all this in detail in the next lecture anyway, but I wanted you to be aware of this diagram, which summarizes all the methods of electric heating that are typically used in industry or even at home. At home, we don't use all of them, of course. We use only a few. Resistance heating is the most common one that is used in domestic applications. But other methods are more suitable for industry. Okay, so I think there's not much left here. Yeah, I'll go through all this later in the other PPT. There's a numerical problem and solution given at the end for dielectric heating. I'll do that in my own notes later. Let me complete this document at least. You don't have to worry about remembering everything. As usual, the assignment I'll send you will have all the things that you will need for the exam. But in the long run, all this information which is contained in these documents is very useful.